Okay, I'm going live now on YouTube, and I think okay, still directing. Yeah, it's starting now. So, good evening, everybody. Thank you for joining this evening. We had our first section in the morning on data visualization, and this evening we are going to continue. This is more like a repetition of what we had in the morning. And just for the rules, please, while joining, please kindly mute your mic so that noise coming from you will not interfere. We had one such scenario in the morning, and I do not appreciate it. And then you will wait. If you have any questions, put it in the chat. And then also, when the presenter is done, and then say it's time for question, you can then go ahead and ask your question. This evening again, we're going to have Prayer and Ajam Hassan take us through data analytics and visualization. And yeah, Prayer, over to you.
Hello.
Okay, yeah, Najam, yeah, go ahead.
Yeah, so hello everyone. We'll start with this session, and I hope you can see my presentation.
Yes.
Like we had spoken to you in the first session, how important statistics is for data analytics for astronomers, and how astronomy is becoming a very data-rich science, and hence we require to use computers and statistics to analyze the data. There are some basic essential statistical tests and methods which are used in astronomy, which I will be touching very briefly in this presentation before we start off with the matplotlib and other things. So topics to be covered in this presentation are foundations of statistical inference, probability distributions, some important ones, essentials ones which are mostly used, estimation and hypothesis testing, Bayesian inferences, bootstrapping and resampling, model selection, some non-parametric methods will be discussed, and time series and multivariate methods. So why statistics matters in astronomy? Astronomical data are noisy, incomplete, and biased. Measurements often include detector noise, selection effects, missing data, censored observations, irregular sampling. And this and modern surveys are generating massive data sets. For example, LSST, Gaia, GWST, SK, and so on. So there's tremendous amount of data, terabytes, petabytes of data flowing in, and it has become essential to use statistics to analyze the data. And statistical methods allow to estimate parameters, for hypothesis testing, and for uncertainty quantifications and pattern discovery, to see patterns in the data and make science out of it. Yeah, so a random variable is a measurable quantity whose value depends on observational outcomes. So a random experiment is an experiment where you have certain outcomes. The simplest example of that is of tossing of coin. When you toss a coin, you get either a head or a tail. So heads and tails, these are the random variables. And when you uh, talk about random variable in the context of astronomy, measurements of stellar magnitudes, measurement of galaxy redshifts, photon counts coming from a certain source, pulsar timing residuals, exoplanet transit depths. These are all examples of random variables. And important concepts we have to know are: what is the probability density function? We look at some probability density functions to illustrate, especially one or two I'll touch upon, which are essential ones in astronomy. Cumulative distribution functions, expectation value, which is essentially the mean, variance, and uncertainties. So the most common, the most frequently appears in nature is the Gaussian distribution, also called the normal distribution, and it is represented. So probability distribution, by that we mean a function which represents how the random variable is distributed, right? So in this case, for the normal or the Gaussian distribution, your function which represents this is given by this expression here, exponent to the power of minus x minus mu by 2 sigma square, where mu is the mean and sigma is the standard deviation. And a Gaussian distribution gives you a perfect bell shape. The one which we see on the right is representing a Gaussian distribution whose mean is 0 and the standard deviation is 1, right? So if the standard deviation is larger, then the bell curve becomes more broader. And if the mu varies from 0 to 2, 3, 4, or whatever, the bell curve shifts to that direction. Uh, in a normal distribution or this Gaussian distribution, the mean, median, and the mode are the same, right? They all are same. And this distribution appears very commonly in astronomy. In fact, in different observations and walks of life. For example, even if we see the heights of people in a certain country, you would see that they obey some kind of a bell curve. Most of them lie at the peak of it, while there'll be very few who are extremely short and very few will be very, very tall. But most others will lie somewhere near the mean, median mode, right? They lie somewhere in the middle. And in this graph, you will see marked points like 68%, 95%, 99.7%. These are the regions where, say, for example, the 68% line, it indicates the data, 68% of it is lying within this range. And the 95.1 indicates 95% of the data is lying here. And the central point where x equal to 0, this is half the number of points lying to the left and half to the right. And this Gaussian distribution appears due to the central limit theorem. The central limit theorem plays a very crucial role in statistics. And basically what central limit theorem says is, whatever the underlying distribution it may it be a uniform distribution, may it be Poisson distribution, binomial, Bernoulli, or whichever, if you take many samples, many samples, and take means of these samples, the means would follow a normal distribution. So the application of this appear in when you are measuring instrumental noise. The noise often follows a normal distribution. Astronomical uncertainties, spectral fatigue residues, all follow some kind of a Gaussian normal distribution. So when you have to get rid of noise from your data, you use this to do that. And in many instances, we use this appears. Next one, which I'm showing you is Poisson distribution. Yeah, one thing before we go to Poisson distribution. Remember that Gaussian distribution, normal distribution, is uh, for continuous data, right? When the data is continuous, then you have this one. A Poisson distribution is given by this expression. Probability of x having the value k is given by lambda to the power of k, e to the power is minus lambda, k factorial, where lambda is the mean of the data. And this is a Poisson distributions are often studied for it's discrete ones. And when generally the counts are very few, for example, the photon arrivals, gamma ray detections, and cosmic ray. So you don't see a perfect bell here. It is a skewed one. And you will see that it is there. The mean lies somewhere here. Mean and the variance in Poisson distribution is the same. In normal, mean, median, mode were the same. Mean and variance have no relation in the normal distribution. In Poisson, you have mean and the variance are the same. And when the mean value becomes very large, then it starts appearing, it starts mimicking, starts looking like the normal distribution. So the key challenges are the low Poisson data often violates Gaussian assumptions. And yeah, so similarly, you have uniform distribution, and if you plot that, it will be just a square flat surface where every random variable has equal chance of it appearing. So you have a square, just a flat one. For example, if you take a dice and throw it, the probability of getting 1, 2, 3, 4, or 5, 6, a die has 6 sides. Each one has the same probability 1/6, right? So that would give you a discrete distribution, but a uniform one. So uniform distributions can be both continuous or random, depending on what kind of variable it is. Suppose you are measuring sizes of masses of galaxies or stellar magnitudes. These are all continuous variables. But when you are counting the photons collected and gamma ray rays which you have detected and so on, these are all discrete ones where you have only discrete values. So point estimation is the basic goal of is to estimate unknown physical parameters from observed data. And the most common estimators are sample mean, sample variance, and regression coefficient. These are the ones which are most often used. These are the simplest ones and the most common estimators. The mean gives you an idea what is the average of it. Variance indicates how the data is spread out. A smaller variance, it signifies mean is a good representative of the data. And the regression coefficient shows you how the data is arranged. For example, you may have data points. You must be familiar of seeing Hubble's uh, data of, he looked at the redshifts of galaxies and the velocity of recession, and he got certain points, and he drew a line which goes through this. So these regression lines are fit to data where you minimize the deviations from it. We'll come to that as we proceed ahead. So from that, we estimate the parameters of how fast universe is expanding, or yeah, what is the right. So this, if the slope is greater, then you get, so you derive parameters from data, and by looking at these regression coefficients and so on. So the desirability of these estimator properties are they should be unbiased, consistent, and it's important that they have good efficiency, and variance should be minimum. If the variance is less, then you realize that the scatter is less, and you get a better uh, hang of these things. We have the least square regression, where you notice here is Vi are the observed values. So suppose you have a different x1, x2, x3, xn, you have observations v1, v2, v3, vn. And we expect that there is a function f of x, which tries to show how this dependence of y is on x. So here what we do is we take vi minus f of xi. F of xi is the estimated value from the function. And you take the squares of the deviations to be you minimized, right? So yeah, so we try to minimize this yi minus, so we try to find a function f where these squares of the deviations is minimum. And you see in this graph, the blue dots signify the observational points, while this red line indicates the function which we are fitting. In this case, we are trying to fit a linear function. These functions can be non-linear. They can be exponential ones, they can be periodic ones, and so on. So it's always best to visualize your data when you have the data you plotted and see the trend. If it appears to be lying in a straight line, then you try to fit a straight line to this, minimizing the squares of the deviation, then you get the uh, parameters from that. So the application of this are varied. It is used in orbit fitting of planets, exoplanets, in spectral fitting. It is used in cosmological parameter estimation and so on. The advantage of this is they are simple and fast. And the disadvantage or limitations of this method is they are very sensitive to outliers. So if they are outliers, which for some reason are oddballs, then your whole regression line can get totally messed up and you may get something. So it's always to do fast um, descriptive data and look at the data and see if there are outliers, remove it before you fit the right function, which will give you a better understanding of the data. Then you have these maximum likelihood estimation, where likelihood estimates are given by this function L theta, and log likelihood is given by this, where you take the log of the function. So you are trying to find a function which gives you the most likely hood of expectation of xi. So given theta I a priori, then you try to find a function which tries to tell you what is the most, you find the most likelihood function which describes the occurrence of a certain things. So these maximum likelihood estimation chooses parameters maximizing these likelihoods. And they are statistically very efficient. They are widely accepted, and natural confidence provide the natural confidence intervals. Applications are found in CMB cosmology, exoplanet planet transition modeling, and so on and so forth. So another important thing in statistics, which is often used, is hypothesis testing. If you have a population and you want to understand the trends and behavior of that population, what is often done is you take a sample and you try to understand the sample, and you try to understand whether the sample is a representation of the population or not. Or in certain scenarios, you may have two different sets of observations. You have from survey 1 and survey 2, and you try to compare both these samples and you try to see whether they are significantly different or they're the same, statistically whether they're the same or not. So for that, you fit set a null hypothesis. Null hypothesis is a hypothesis where you don't put a bias. You, for example, when you are testing two samples and we are testing the sample means, the null hypothesis says that the two samples are the same. There is no difference between the sample parameters of one or the other. That's a null hypothesis. And you have the alternative hypothesis where you say sample one has a higher mean than the other, or so on, or the other way around, right? So you either accept or reject the null hypothesis and you accept and do it at certain level of confidence. So there are possible errors which can come out. Type 1 errors are the false positive ones, and type 2 errors are false negative ones. For example, if you wrongly uh, think that a certain object belongs to a certain category, and it is not, then it's a false positive one. And the false negative one is when you reject that it belongs to that category. When it is, then it's the false negative. For example, in the COVID times, we were very familiar with this thing, where when a person is tested and the person doesn't have, say, COVID, but if the test shows that he or she is positive, that's a case of type 1 error where it's a false positive. And the false negative is the person does have, say, COVID, and he's tested as he doesn't have it. So that's type 2 errors. So you have to keep an eye on these errors, and which are very important. And the important quantities to look at are the significant levels, and at what level of significance we are accepting or rejecting the hypothesis at 95% of confidence, at 99% or so. And that is done by looking at the p-values and the statistic which you calculate. So there are different statistical tests I use. Some of the common ones are the chi-square goodness of fit. We have Kolmogorov-Smirnov distribution comparisons. You have Anderson-Darling's tail-sensitive comparison, likelihood ratio tests for nested models, and t-tests. So astronomy examples are source detection, population comparison, spectral model selections. And as we go ahead, I'll give you examples of those when we come to t-tests and some of the tests which we'll be discussing. One very important theorem in statistics is the Bayes theorem, which gives you a method of calculating the conditional probability. So if there is a random variable, an event theta, you find out, in the classical case, you find the number of times that event can occur and the total possible outcomes of it. That will give you the probability of that. But suppose you have a prior knowledge of certain thing, then you use the conditional probability, and which is given by this thing. So in fact, p theta slash x indicates the probability of theta occurring when x has occurred. For example, if I'm rolling 2 dice and I'm seeing the sum of the 2 dice. So a dice has 1 to 6 faces to it. It's numbered 1, 2, 3 to 6. So when you are throwing 2 dice and adding them up, the minimum you can get is 2, and the maximum you get is getting 6 on both and getting 12. So between 2 to 12, you have all possibilities: 2, 3, 4, 5, 6, 11, and 12. And you can find out what is the probability of, say, getting 2, right? So getting 2 is only 1 in these 36 ones. So it's 1 by 36. But when you are looking at what is the probability of getting, say, 5, then you can get 2 and 3 and 1 and 4 and 4 and 1 and 3 and 2 and so on. And you will get 4 by 36 and you calculate the probability. But suppose you know that the experiment has occurred, and you know that an even number has happened. So then what's the probability that it is 5? So obviously it will be 0. So conditional probability is when you know what an outcome is. And suppose you know that outcome is an odd one, then the probability of calculating what 5 is changes. So this is what this gives. And the Bayes theorem is a very powerful way of calculating probabilities when a priori we know certain things. Okay. So a priori knowledge changes your methods of calculating the likelihood, the chance of certain thing is happening. So you have the priori probability, likelihood, and posterior distributions, which you have to keep an eye on. And the advantages is it includes a priori information. The classical ways of finding the probabilities, you have no idea, no information about the thing. But here, once you have certain knowledge about the system, then your ways of uh, probability of calculating certain thing occurring or not changes. So, for example, suppose I know what are the chances of a supernova uh, uh, happening in a solar neighborhood. And suppose I have data of the last 20 years and know how many supernovas occurred, then if I have to calculate what is the probability that it will happen the next 10 years, it changes if I have a prior knowledge of what is the frequency of it happening in general. So it produces full parameter distributions and it's excellent for complex models. And the applications again are many exoplanet orbital solutions, cosmologically inferences, and gravitational wave parameter estimations, and so on. So they are very varied. And another thing which is used a lot these days is the Markov uh, chain Monte Carlo. So these are MCMC. You do simulations and you uh, these are used to estimate parameters of various models, and these are used a lot in cosmology. And the popular algorithms are Metropolis, Hastings, Gibbs sampling, Hamilton, Monte Carlo algorithms. And the output we get are the posterior distributions. It defines you the credible intervals where you can restrict your parameters to, and it can give you a chance of parameter correlations. And so the astronomy tools which are used very often are the MC, PyMC, and STANS. And yeah, so bootstrapping resampling is also a very important aspect of astronomy used in astronomy. And the idea behind bootstrapping is to generate synthetic data sets by sampling without replacement. So when you have small samples or missing data, you try to recreate by using bootstrapping methods. These are used to estimate uncertainties, to build confidence intervals, to evaluate model stability, and so on. So advantages are there are few assumptions. It works for complicated statistics, and the limitations are they are very intensive computationally and can fail for correlated data. We have been discussing the parametric methods now where you know an underlying distribution was the random variable follows. But in case of where we don't know what is the underlying distribution, whether it's a normal distribution, Poisson or uniform and so on, when we have no idea, then we use the non-parametric methods. And examples are these median statistics, rank correlations, kernel density estimators, and so on. And the applications are to find luminosity functions, galaxy color distribution, stellar population studies, and so on. Other methods which also are being used a lot these days are the clustering and classification techniques. And there are k-means clustering methods, hierarchical clustering, support vector machines being used, random forests. And these are being used for galaxy morphology, classifying galaxies. For example, you have a zoo of galaxies collected from a survey, and you have to um, bin them up as ellipticals, spirals, lenticulars, or irregulars. And we are trying to do it using machines then you use these clustering and classifying algorithms. You train the machines. You train them to show them many images of, say, elliptical galaxies, then train the machine to identify this and bin them as an elliptical one or a spiral one, and so on. So once they are trained, then you can use the machines to uh, do the classification. Similarly, there can be examples where you want to find, you are observing, say, certain regions of the sky, and you want to find out the embedded star clusters in the field. And you use these clustering algorithms to find clusters from a set of uh, stars which are observed between certain RA and DEC and certain parallax, and you can define conditions which will define what should be the distance or the nearest neighbor method has to be used to identify grouping clusters of this, and these are being very successfully used to look at crowded field areas and define membership of stars and find members, non-members from it. So this is big used in galaxy morphology, variable star classification, transit detections, and so on. Then you have the time series analysis, and where you have continuous data coming from a source, and you have to study detect the periodicity of it, identify the transient events from these, and to model the stochastic variability in it. The common techniques are the Fourier transforms, wavelets, autocorrelation analysis, and applications again are there in many areas of astronomy, to name a few: exoplanet transits, pulsars, age invariability, and so on. So, practical advice for researchers is it's very important to understand assumptions behind every method, and it's very important to visualize the data before modeling it. And we can use simulations and bootstrap validations, right? Once you've got results, you can run simulations and verify and reconfirm whether what you've achieved is validated by simulations as well. We should try to avoid overfitting. And it's very important to report uncertainties very carefully. If there's uncertainty into the data collected or methods, it has to be very clearly specified. And reproducibility is essential. Should have to have repeatability, and you should be able to reproduce those results again and again, or as and when required. The recommended software is Python, R, Stans, or PyMC. What we shall be using mostly in these sessions is Python, in which we'll be using NumPy, SciPy, AstroPy, Pandas, and so on. So, in summary, astronomy increasingly depends on advanced statistics because astronomy has become a data-rich science. Classical methods remain useful but have limitations. It's become essential to use statistical methods and computers to analyze this data. Bayesian and computational methods are now central to statistics. Non-parametric and machine learning methods are growing rapidly, and careful statistical reasoning improves scientific reliability. Right. So with this, I will come to the next part of my presentation where, yeah, there's a raised hand. I'll just see there's a question. Just a minute. Uh, I'll just see if there's. Would you like to see? Yeah, I'm just seeing there's a question there. I can't see.
Jim, are you asking for questions?
Yeah. So I guess the data, what could be an example of a situation where data is missing in astronomy? So many a times when you download data from the archives, you may have, say, names of various, say, clusters, and you may have their right ascension and declination, and you may not have radial velocities for certain. Yeah, you may have if you have spectroscopic observations for those, you will have the radial velocity, but for certain objects, certain stars or so, you may not have that, right? So it's very often you find where there is missing data, right? So you have multi-parameter tables where you have their positions, their metallicity, their RA, deck, parallax, and various things, but for you may not have this for all the objects. So very often what happens is in this large table of data, if you siphon out only those objects where all the columns have entries to it, then you are left with very little of them. So there are different ways of filling these missing data points, and bootstrapping methods, very sophisticated methods, are used to find these missing values or replace them with others. Yeah, so you will yeah, so you can have, say, like I said, you have their positions, RA, deck, parallax, but you may not have their radial velocity for certain objects. Yeah, you have a star cluster with, say, uh, uh, 200 objects or 50 objects, and you may not have uh, radial velocities for all. You, I guess the data set of stars of different ages and clusters of different ages. Yeah, so you may have different data sets of stars in different regions of a galaxy, and you're trying to compare their things, right? So you may have different types of uh, clusters uh, and have different. Yeah, so yeah, somebody has also answered it. Yeah, yeah, okay, yeah, okay, right. So now I'll get on to the. Yeah, are there any? Are there some limitation to PSAS clustering?
Is visualizing part of this?
Visualization of data different from same as modeling of data? Yeah, they are different things. Visualization is you have data and you try to uh, uh, by doing some basic plotting, you can see what's the trend of the data. By doing a little bit of statistics, right? So you visualize it by uh, by by doing graphs, plotting, doing scatter diagrams, or you're fitting curves and so on, and trying to visualize how the data is spread, right? Whether it follows a Gaussian distribution, whether it is a linear fit, whether it's a sinusoidal one. Yeah, so that is visualizing. The data modeling is you try to model the data with certain functions. So there are times they are similar, but they essentially are two different things. One is you are modeling the data. Other one is you are trying to visualize it by using by plotting it and so on. So beginners tutorial, we'll have a look at Matplotlib, and here we learn how to create some basic plots, how to customize these plots by putting, say, uh, labels to the x-axis, y-axis, putting legends, drawing grids, and so on. And then we'll see how to have multi-plots. There are times when you want to either plot the same two functions in the same graph, or you want to have them separately as a mosaic of two or three different ones, uh, in a single column or in a single row or two columns and two rows, we'll see these. Then we'll see how to create bar charts, scatter plots, histograms, pie charts, and so on, and how to add these titles, labels, and so on. So we had seen a little bit of Matplotlib in our previous sessions too. We import Matplotlib plot as PLT, and we import NumPy as NP. We are importing NumPy basically to be able to create data sets. Yeah. So the simplest one which I have here is I have X and Y two lists 1, 2, 3, 4, 5, and Y also has same number of points. The length is the same. Values are 2, 4, 6, 8, and 10. And I do a plt.plot. And when I plot it, I get this straight line, right? But if I um, say uh, PLT, yeah, uh, yeah. So when I say PLT title, when I say plt.title, I am creating a title to that. So whatever you write in these inverted commas, you get that. And when I say I put PLT X label and PLT Y label, uh, I get the X label and Y label here. And when I say I put plt.grid equal to true in the, then I put a grid as well in it, right? So the most simplest one is where you do not have PLT title, X label, and grid, and just plt.plot X comma Y, it's going to be plotted. Suppose I had another variable, say Z equal to 3 comma 9 comma 12 comma 16 1 2 3 20, same number of points. And I also have plt dot plot X comma Z, and I plot this, I'm getting both the plots here. Yeah, one is, so the program itself decides to change two different colors to illustrate this, right? Further, we can add legends to this and so on, which we shall see as we proceed ahead. And if I run this command plt.scatter, it will give me a scatter plot. Similarly, if I say plt scatter with Z, I get the scatter, right? Scatter plots. Okay. So customizing, we can further customize by specifying the line style. We can specify the line width. We can even specify what kind of a marker do we need. And right, so I am using this numpy's linspace function to define a variable x which goes from 0 to 10 in hundreds of, equally spaced 100 points between 0 and 10. And y is np dot sign of x. And I'm using plt dot, right? So suppose I don't have these things here and I run it, I'll get this sine curve. Okay. And you have this PLT title, X label, Y label, and which is giving you the X and Y label, whatever you specify there. Now, if I so if I specify the line style and I change the say to dash dash, and I plot it, you see that you are getting dashed line there. And the markers also, I can change it to, uh, say if I put a plus there, then I am getting it with plus and so on. So there are various markers which are possible, colors you can choose, and you can and do that. Okay. So this is another one. Multiple lines in one plot we have already seen. And here we have PLT X NP sine and NP cos. So we are plotting X against sine and X against cos in the same one. And I'm specifying the title as sine cosine. X label is X, Y label is Y. And I say PLT legend and grid true. So if I specify that, then a legend also appears here. A legend also appears here. And again, look at the scatter plot. Now I'm doing scatter plot with two variables which I'm randomly generating, X np random dot rand 50 points of that, and Y also randomly generated another 50 points of that. And when we do a scatter, PLT scatter, you will see that you get a scatter plot here, right? So you can specify the title, labels, and put the grid on or off if you wish. If you want a bar chart, especially which is done for when you have different categories. For example, I have categories ellipticals, spirals, lenticulars, and irregulars. And there are 5 ellipticals in a survey, 7 spirals, 3 lenticulars, and 8 irregulars. I run this command plt.bar categories and values. So from values, it's picking up these values, and from these categories, it's picking up the categories which we have here. And the rest are known commands, title and labels. And when we do it, we are getting the bar chart. Okay. Suppose we had, say, A, B, C, and D, some 4 different categories, and have some values like 15, 13, this, and run it, you are getting, yeah, you are seeing A, B, C, and D, and it is for each A how many are there, and for B how many are, right? So these are and the command is very simple, plt.bar, and it requires the categories, and you require the same number of values. So if you have more categories, and suppose I don't have this one, and try to run this, you get an error, right? Because you don't have, there are 4 categories, but the values are only this. So you require to have same number of entries in both, which can then get plotted. When you come to histograms, the command is plt.hist, and I have, say, data with NB random numbers 100, and I do the plot here, and I can change the number of bins. Yeah, if suppose we don't write what the bin is, I don't write what the bins are and run it. I will get the default ones. It gets binned by a default one. But when you specify what the bins are, right, it can be 10 bins, it can be 30 bins, whatever. And it breaks up the data from the lowest to the highest in 30 bins, and it plots you gives you the histogram. And these are the title, PLT title, PLT label, and so you're putting frequency on y-axis values here. And it's not difficult to guess how a pie chart will be done. plt.py, and you run these with, say, ellipticals, lenticular spirals, and the sizes are 45, 40, 10, and 5. And I'm plotting labels as labels, and this is specifying to specify the percentages in terms of a floating point number with one. Yeah, it is f is the floating point number, and after the decimal to have only one value. So when I run it, it is giving me in this way. Double ellipticals are 45%, lenticulars are 40, spirals 10, and irregulars are 5. Okay. So this is for the pie charts. And coming to subplots, we use this kind of a command, fig, axis, plt.subplots, 1, 2. This signifies there is one row and two columns. And the figure size is specified here. What should be the width of it and what should be the height of it. Even if you don't put figure size, you will get it, but some default sizes are given. But to beautify it and give it into a form which you like, we specify whatever sizes we prefer. Yeah. So suppose I take this as 10 and 4. Oops, it has become too small. Yeah, so you specify what should be the width and what should be the height of it. Anushka raised her hand. What does he say?
Could we generate a 3D plot? That is one this thing. Yeah.
3D plots. Yeah,
Why don't we let
we will
PRT
be.
show it? Does it to show the PRT show up with brackets? When do you put that, when do you not?
Yeah, so another thing which we are, which is interesting to see is, for example, when you have to do, say, a histogram, you may not know what is whether you should write hist or you should write histogram, the whole word, right? So since we don't know, I'm trying to guess. So plt.his and press a tab. And when I do that, I get hist and hist2d, right? So hist is the function, and we specify what's the data is, and we specify, yeah, so the data, and you do it. Right? So suppose we have another data set, data 2, and np dot random dot rand n, and again I'm creating another randomly some data, another one. And you recall there was a data, there was a hist2d also. So I'll comment this one, and I will run this with data and data 2, right? So you require 2 data sets, and with bin 30, and this is what your hist2d gives, right? So you have 2 data sets, and we are getting the frequencies of both and doing it, right? So these are the things. And subplots, similarly, we can, yeah, another important thing is how to save these figures into a file, because you may, having plotted something, you would like to save it as a PNG file to be sent to be added in in your thesis or your article or so. And you save it by using plt savefig, plt.savefig, and you specify the name of the file in which it will get saved, right? So if I say my plot one dot this, so I'm plotting x against y. X is NP length space 0 to 10, 100. Y is x to the power of 2. And I'm plotting x against y and saving it to a figure, right? So PLT save figure, and when you execute it, I am also putting show PLT, so it is showing the screen, but it is also saved. It is also saved in the location from where I'm running my Jupyter file. So if you go to the location where from where I've invoked this file, you will see my underscore plot one PNG here. And there it is. So basically here we have learned the basic plotting, plot customization, scatter plots, bar plots, histograms, pie charts, subplots, and how to save figures. I've given some exercises here. And there is yet another notebook which I will share with you, where it will show you how you can, in Matplot, have multi-plots which can be saved here. Okay, what is Anushka say?
Is it not Anushka somebody else? For a histogram, if we have continuous data, how will we choose the bin size?
How do you say this bin size? You change the bin size exactly like bin equal to whatever you specify, right? So
How do you choose it? How do you choose it?
how do you choose it? Yeah, you choose it. There was a question is how do you choose the bin size if you have continuous data, right? So that uh, first thing is you run it with default and see whether the histogram is representing, trying to show what it is, right? Then you can choose your different bins to see the trend better, right? So if you make the bin size too large, again, it's not very good, but you can find an optimum one, right? Suppose they are 0 to 20 points values, and you choose say uh, 20, then it breaks up into one each. Yeah, you can choose 2 or 3 and choose one which makes you gives you a graph which is meaningful and all. Yeah, so it's up to you to choose what it is, and depending on what you're trying to see in from the data, you can play around with the bin to see which is the most appropriate one. So coming to the second Matplotlib multiplot tutorial, you can see that you can create multiple plots. See, if we had seen only one row and two columns, here's an example where we have two rows and two columns. And in one, I have the sine, other I have a cosine, third, I have the random noise, fourth, I have some damped oscillation. And the way we do it is we have PLT subplot 2, comma 2, right? So this is for two rows, two columns. And we had this x and p is your x variable. And using that, I am plotting sine with the red, is a sine wave title, and axis 0, 1, 2, and 3. So 0, 1, 2, and 3, right? So it tells you which one has to be plotted where, and you specify even the titles and legends and all exactly the same way. You say axis 3 dot set title. So damped oscillations will come to the third one. Yeah, so 0, 1, 2, and 3, right? The array starts from 0 and do it. Similarly, you have another example here.
Yeah. How to get access title and label in multiple plots. I think you've done that.
You'll be doing it.
The question you saw,
How do you
it's there, the text, man.
access title? Yeah, so you do it the same way. Suppose I want to put an access title here. I say
Yeah, it's there.
axis
It's there, it's there.
axis title is given there. But if you want the
Exact title.
yeah, so you specify axis
0, 1, 2,
and
3, whatever.
say 1 dot
It's there.
you set the X label and you specify whatever, right? So set X label, no? Set X label.
There's already a label. PLT is not defined, it's saying. It's saying PLT is not defined. Matplotlib or branch.
Set,
Matplotlib as PLT.
yeah. Set, just a minute. PLT. Dot PLT dot. Okay, I'll just have a look and specify. I'll just show it.
I'll show it, it's there, Matt.
Yeah. So in fact, Priya ma'am will be covering that. So she'll show how to set the labels for these. Yeah. So you have here, for example, figure dot soup X label, right? So you're setting the X label and Y labels, right? So this is the way you do it. Figure dot soup X label and figure to soup Y label, and soup will do it for the whole block. Yeah, so this is one way of doing this. Yeah, for the whole figure, you define these labels. Okay, so with this, I will stop, and Priya will continue. I'll come back after a while.
Yeah, so hello everyone, and I will continue from where Sir stopped, but there's going to be an overlap, obviously, between what we're going to be doing, and I hope that's okay. So now I hope you can see my screen. Yeah, can you see my screen, Naja?
Yeah.
Yeah.
Yes.
Okay. Yeah. You can see this, right? Visualization. Yes. Okay. So what we've been talking about today is basically visualization. That is, like we already spoke about, that in astronomy, we basically have a lot of data, right? And to describe the data, there are two ways of describing it. One is by visuals, which is you do plots, various kind of plots, which is to describe the data. And then another very powerful tool to describe the data is statistics, right? Which we already spoke about. Sir spoke to you about it as to what are the different kinds of tests, etc., you can do to describe the data that you have. But now we are going to focus upon the visualization of data, right? So Sir spoke to you already about Matplotlib, which is the very basic plotting package which is there in Python. And Matplotlib is the original, the most basic one, which basically works with NumPy arrays, and it can plot them all very well. And it is the basic one. But then today, now I'm going to talk about another library, which is called Seaborn. Okay, Seaborn is also a plotting library which is built on top of Matplotlib. Now, because it was built on top of Matplotlib, it is, aesthetically more pleasing. It could be more informative, and therefore there's lesser code. There are more libraries and all in that, which we'll see that why it makes it more simpler. Now, typically when you're running Seaborn, it is best to run it with pandas data frames. Okay, it's kind of Seaborn is compatible with data frames, pandas. You can use it with other things also, but it's almost kind of a given that it's better to run it with a pandas data frame. So if you're handling astronomy data with which you want to make complex plots using Seaborn, then preferably do it with a pandas data frame. Okay, that's the way to actually do it. Now, yeah. So what we're going to see about, you've already been talking about it, as how do we actually do this, and we'll go about it. So first of all, we're actually going to simulate some data. This is the standard, the way you call the libraries: matplotlib.pyplot as PLT, Seaborn is generally called as SNS, NumPy as NP, and pandas. And here we are actually going to do some data simulation code where we are going to simulate data which we are going to use for the plot. So the first plot which you can see is basically we have 100 stars, okay, for which we are going to generate stellar masses. Okay, for these stars we are going to generate the masses. Now the thing is that when you generate random numbers, we spoke about that last time also, that there is a random number seed. Okay, and the random number gets generated between 0 and 1. Okay, always that's the range. What you have to do is, supposing you want it from 0 to 100, then you will multiply that into 100 so that it gives you 0 to 100. But otherwise, by default, it does it from 0 to 1. So now here what happens is we are generating the masses to be random numbers, but we can also give an underlying distribution. Today you did sit with Sir, you did various distribution functions. For example, you did normal distribution, log normal distribution, you did Poisson distribution. So that you can generate your random numbers so that they have an underlying distribution. So here what we're doing is we're generating stellar masses, which are random ones, which have a log normal this thing. So that's generally for stellar masses, the mass function of stars. It actually follows a log normal distribution. And that's why we are putting log normal, where we're saying the mean is 0, sigma is 0.5, and the size is the number of stars. And then we also generate the luminosity of these stars to be there is a mass luminosity relationship, okay, where the luminosity of stars is basically mass to the power of 3.5. Okay, this is a thing which we know from stellar astronomy. Okay, it's a theoretical thing where the luminosity of a star is proportional to mass to the power of 3.5. And that's what we are doing. We are doing it stellar masses to the power of 3.5 into some random listing. Okay, we are also generating some variable stars because this is one kind of data, but another very important kind of data set which we have to handle now in astronomy is about variable stars. Okay, so when all do we use variable stars? One could be, for example, if you're analyzing exoplanet data using Kepler or TESS. These are two NASA satellites which basically look for exoplanets. In them, you basically get what are called light curves. That means you'll see a difference in the brightness of a star with time. So you'll get variable brightness. You could also have a variable star, maybe a Cepheid star, or it could be an AGN, active galactic nucleus, which is showing variability. So we're just seeing a typical thing. Number of time points are 50. The time points, we are arranging them in that. And the brightness signal is 5 plus 2 times. It's a sine curve. You see NP into sine. Time points by this. We are adding some noise factor also, which is a random normal distribution, and variable star brightness. We also generated some kind of redshifts for galaxies, 500 galaxies, where the redshifts are just random numbers with a gamma function. And we're doing, for example, we are also plotting different object types. We star, galaxy, quasar, nebula, star cluster, where you have some counts of it. And we're doing another data set for exoplanet properties, where we are characterizing what kind of an exoplanet we're looking at, gas giant, supergiant, Neptune-like, etc. Right? So we just run this to get the data sets. Okay. Now what we are going to do is, this will be slight repeat of what you already did with sir. If you remember, the plotting area is called a figure, right? Somebody had asked question for subplots, so I'll basically see this. The thing is, your figure area can be broken into subplots. What are subplots? For example, you want 4 plots to be put 2 and 2, or you want 3 plus 2. You want to have these, so these are called subplots. In your plotting area, you want to break it into some other plots. So for example, you will say plot subplots, right? And then what do we do is that you can, for example, each of your pieces will get a certain number. So for example, once you have these axis objects, these are the individual ones, you could have axis, scatter plot, histogram, whatever. So for example, look at this plot. We have simulated star masses, star luminosities. I am saying plot subplots. If I wanted it to be, say, 2 by 2, I would have had to write it over here, 2 into 2, 2 comma 2. But here I have left it default, so that is a single one. And I'm drawing a scatter plot. So the plot is called axis. Otherwise, if you remember when you did it with sir, you did AX1, AX2, AX3, AX4. So in that way, each of the plots gets numbered, right? But in this case, since we have only one plot, it is just called AX. And you set X label, set Y label, set the title. It's only for one. So here's my X label, my Y label, and here's my title. What sir showed you also was that if you had put this, supposing 2 by 2, you'll have 2 plots. So then you'll have one thing called AX1, AX2, AX3. And with that, you refer to each of the individual plots. Okay, so for the individual plots, if you want to add a label or a title or whatever you want, you will accordingly refer to it as AX1, AX2, AX3, etc. Okay, and you plot it like this. Okay. You could even have, for example, so this is a plot for stellar mass versus luminosity. You can see you're getting a plot like this. If you remember, I told you that luminosity is mass to the power of 3.5. So typically over here, you're getting this 3.5. But if you had converted this to a log plot, then you would have got a straight line. Okay, so you can try that out and see it. Similarly, here we have a scatter plot of exoplanet period versus radius. Okay. So we are looking for a relationship between the period of the exoplanet to its radius. Okay, so here is the radius of the exoplanet in Earth radii, and here's the orbital period. Now what you can clearly see is that we do not see a very clear correlation between the two. You can actually use a statistical test to actually look for correlations, or for example, such a plot is suggestive that there does not exist a correlation between the exoplanet radius and its orbital period. So what happens is, like we earlier said, that basically a picture speaks more than 100 words. So one is your numbers which you get from statistics, and the other thing is what your plots convey. So if here I want to convey that exoplanet radius has got no relationship with its orbital period, this is a very good plot to basically show that you're getting such a scatter plot that it's obviously you cannot be fitting anything to this, right? Now let's look at a line plot. We are going to do a line plot, which is a line plot means we join all the points by a line, right? A scatter plot, you just put them. Here we join all the points by a line. So that's what is called a light curve. And this is what we do for light curves. Like I told you, in your CAP projects, when you could be either using exoplanet data, then you could be using light curves, or you could use it for some variable stars, some Cepheids or stuff like that. And again, you'll get curves like this. Now, ideally speaking, I think sir showed you some sinusoidal ones, etc. Ideally, that is what we would expect from theory, right? But in reality, obviously, objects do not behave like that. And therefore, what happens is you end up with a plot like this, which it kind of resembles a sinusoidal curve, but it's not a sinusoidal curve, right? But it kind of resembles. So that's how you get this kind of plot, right? If you want to see a light curve. I can also plot histograms. You already saw this. This is from all my galaxies. I'm putting a redshift. I'm getting the histograms, right? So this is for different kinds of objects. These are number of stars, galaxies, quasars, etc. I may put in various things. You may actually add in, how would you actually add in other things? Labels, titles, legends, appearance. You could add it on this and see this. This thing is given to you so you can have a look at it. You can also see this one for exoplanets. This has various data sets for exoplanets. And you can see that over here, we have, you see that we have different exoplanets in it, of which all of them have different types. You remember, we had put different types for them. And you see unique types, which is type. If you remember here, we had written, right? We had written whether they are Jupiter-like or they are, where is it? Yeah. You see the types are these: gas giant, super Earth, Neptune-like, right? 3 types we defined. And therefore here what you do is, in this plot, I can define this thing, which you can see the planet type, right? And unique types is this in the type. And for different types, I may put different colors. So now when I'm making this plot of radius versus orbital period, remember we already looked at this plot earlier, radius versus orbital period. Now what you see is we have plotted differently in different colors for planet types. It could be that we are trying to see that is it that there exists a relationship between the radius of the exoplanet and the orbital period for different planet types, individual planet type, because we had it all mixed. But now also here you see that when we separate the types also, you do not see a very clear, a clear trend, right? So you made this thing. So these are the kind of basic plots you can have with Matplotlib, which you also saw with SERP. But now we will move on to Seaborn, because that's basically what I'm here to be doing. So Seaborn, like I told you, it is basically made over Matplotlib. So it basically, it's basically there to make your plots look more appealing, more nicer, and it does things much more beautifully. So you'll actually see that there is a default styling which it has, and it integrates very easily with data frames. And therefore, generally, the data which you're plotting with Seaborn, it's good to actually do it with this. So here you see the same data set which we had. This is exoplanet data set of radius versus orbital period. You see that I can plot it over here, and this is the plot over here which we've put. Okay, I could also make this thing. If you remember, we did it by type. Here you could actually add this factor called hue, right? If you remember, in the earlier one, we had actually put it like this, where we said unique colors is this, and we said unique types is this, and like that, right? That's how we made the different colors. But here what you can do is you can add another factor called hue, which is, you say your hue is for type, right? Your X is orbital period days, Y is radius of the Earth, while hue is the type. And therefore, by it actually puts different colors for the different types, the 3 types that we've defined: gas giants, Neptune-like, and super Earths, right? All of them get defined like this. The Seaborn histogram, see how they are different from these, is that you can see it's quite different from the one that Matplotlib generated. If I'll come up here, here is the Matplotlib generated histogram, which I had, which you have over here. But if I do it with Seaborn, I'll show you further improvements also of this. You can see here is the distribution of galaxy redshifts. Okay. The bar plots can be similar to that, slightly different. And you could have your subplots, right? We've listed some exercise over here, so you can have a look at these exercises and try to make these plots. Now, actually, what we would like to happen in this thing, okay, this is the visualization. I will open another notebook, which is my Seaborn one. I have another notebook for Seaborn, which is specifically with astronomy examples. So what we'll see over here is, here again there is a artificial catalog which has been generated. So for example, here I have generated, there is some data set where we basically have 3 clusters, okay, A, B, and C. For these 3 clusters, we have the group name, RA deck, their distance, parallax, proper motion in RA, proper motion in deck, age, mass in M-sun. This is the color, the magnitude, and the disk class. Okay, so this is the data set which we actually have. So for example, if we do it with Seaborn, when I do a plot, I'll do a PLT figure, right? And I say SNS scatter plot. You see in one line everything comes. This is my data, which is the data frame. This is my X, this is my Y. The hue is varied based on the group. If you remember, the first column is the group. So if your group is different, you get into a different hue or a different color. The style is for group, and you put in these factors. So you see here my 3 different clusters have been identified, A, B, and C, as per the table, which I had in the table. Okay. I mentioned this earlier also. Another thing you need to be careful about when you're making plots for your papers is that typically here we have the pleasure of having a colored screen, but often people who may read your paper, they may have only a black and white printer. So when you're plotting, for example, A, B, C, 3 different clusters, ensure number one, here what we've done is we put them all in 3 different colors, so very nicely it shows up whether it belongs to A, B, or C. But the other thing what you should also do is also do it in terms of markers, right? So for example, if you see A is put in circles, B is put with crosses, and C is put with squares, so that in case the person, whoever prints this your paper, if they print it in black and white, they'll also be able to notice it because of the difference in the marker. So always be careful about the plots that you make. It is nice to have good colorful plots, which you should make, definitely. But you should also try to make your plots color independent, in the sense that if a person prints it in black and white, then he or she should be able to still differentiate, right? So for example, in this plot, it has been done so that you have a different marker. So you see what we put is style as groups. So for different groups, you can see you have a different this thing. If I don't done that, then all of them would have had the same thing. I can remove that if you want and show you that. If I remove that, then now you can see all of them are the same points, right? They're all circles. The default is circles. But now if I put it like this, I am getting a different shape, right? So that's what you need to do to ensure that your thing works. The next thing is, now let's go to proper motions. If you do proper motion, here we have not done this thing. You see the style is made for disk class. The style is not made for groups. And therefore here we have 2 different things for disk class. What is the disk class? That means if the star is with a disk, or it is diskless or disk bearing. So therefore diskless is the one with the circle, and disk bearing is the one with the cross. But you can see that the clusters are all different colors, but not different markers, because the marker, the style has been differentiated based on disk class. So you can see that this has come like this, and therefore here in principle, they don't differ in the marker, because the difference in marker is coming for diskless and disk bearing. Okay. We've also done a CMD. If you want to do a CMD, this is artificially this thing, that's why your CMD looks quite bad, but that's because this is artificial data. So it's using the color BP minus RP and the magnitude, which is G magnitude, and plotting the color magnitude diagram. Okay. We can also do very nice histograms with Seaborn. For example, look at these histograms. We've made 3 histograms for these. The histogram is for distance distribution. So what is it on x-axis is distance. And what you can see is that you plot these, and then you have this thing. This is called a kernel density estimator, a fit which comes onto each of these histograms, which shows you where the peak is lying and where does it this thing. So you have KD equal to true. If you had false, then you would not have had that curve. And you can put it like this, so that the hue is by group, and the distance is this. We've put it in 35 bins. You can change the number of bins. If somebody had asked a question on bins, so you can even, for example, with bins, you basically have to play around with it, right? So now if I made it 25, I got this. I may even make it 20. I've reduced the number of bins, so my thing has become this thing. If I increase, you may see that now if I make it 40, for example, then you will get a lot of variation coming like this. So actually, it depends upon how you want to, your data, how do you want it to convey, that you should accordingly choose your bin sizes, right? If I do not want to show a lot of these variations, I may just go for a bigger bin size, so that I'm just getting something smoother, right? If I want something smoother, but if I want to show the variations, then I may keep smaller bins. So you have to actually choose it as per What do you want to convey with your data set? Okay. Last time I think we spoke to you a little bit about these kind of plots, which are very important plots in astronomy. These are called box plots. So box plots are what? For cluster A, B, and C. I have these three groups, right? I'm going to make a plot of the total proper motion, okay? And what you see, this is called a box plot. So in a box plot, this middle point is the median value. The first upper part is the Q1, that is a 25% quartile. This is the 75% quartile. And then there's a difference, Q3 minus Q1. And 1.5 times of that, I put these. These are called the whiskers, okay? And so once I put this, anything which is an outlier will come outside this, right? So what I do is I plot it like this, and I look at my points, and if everything comes in this, it's fine. But if it comes outside, like you look over here, there's a point, these are points outside. So these are examples of outliers because they are outside 1.5 times Q3 minus Q1. That is the definition of an outlier. So these guys are outliers, but otherwise you don't have outliers in A and B. This one is an association, hence you have these outliers. Okay. Now you could also have, these are the box plots. You could also have what are called violin plots. In violin plots, this part is basically giving me the distribution of this function. So for example, mass is there. So it's giving me such a distribution of masses. That means the peak is somewhere coming over here, and then you can see this kind of a distribution. Like I told you, the mass is basically more of a log normal kind of distribution. It's not obviously a normal distribution. So you'll get something like this for masses. Okay. You could also, another very important thing in astronomy is to plot what are called pair plots. Supposing in your data, for example, look at this, we have 5 columns. One column is distance, one column is proper motion in RA, one is proper motion in deck, this is BP minus RP, and this is absolute G, right? So these are the 5 columns I have. Now, supposing I want to ask a simple question, are any of these columns related to one another, right? So I basically want to plot distance versus PMRA, I want to plot distance versus PM deck, distance versus BP minus RP, distance versus this, versus each of the things, so that I want to check are any of them correlated, right? So when you do that, you actually, this is called a pair plot. So you end up with a matrix like a grid, where here you see, I write down all my columns. You see, this is my first column, which is my parallax, then I have PMRA, PM deck, BP minus RP, absolute G. This is the distance. So what do? This first thing is going to be distance versus PMRA, PM deck. So this is distance versus distance, hence I just do a distribution. Then I do distance versus PMRA, distance versus PM deck, distance versus this, distance versus this. Similarly, I plot it in this. These are symmetrical. So this one is the same as this one is the same as this. I can draw it symmetrically, right? And therefore, this is what is called a pair plot. So this will actually show me if there's a relationship between any of these parameters, okay, which you'll be able to see in these plots. In this case, I can tell you in advance itself that these parameters are not related to one another, hence you will not get a relationship, okay. Now, for example, another important kind of plot which we do is called a heat map. A heat map is exactly like a pair plot, but instead what happens is we use what is called the Spearman correlation matrix. That means if I want to know if two things are correlated, I define statistically what is called a Spearman rank. Now, a Spearman rank is what? It is, for example, if I plotted distance versus distance, right? Here is distance. So distance versus distance is this. It's obviously 1 because distance is, it's to itself, it's 1, right? The second column you can see is parallax. So distance versus parallax is minus 0.93, right? Why is it minus? Because the distance is actually 1 upon parallax. So it's a negative correlation. Ideally speaking, it would have just been that, but with Gaia, etc., there are some more factors which come in. So distance is not directly 1 upon parallax, and therefore you can see the correlation is 0.93. It's not 1, it's 0.93. So distance is related to parallax. So this is like our pair plots, but here I can see through the heat map that Red is super correlated, that means 1. Then this one is also correlated, but it is a negative correlation. So if you see over here, the red ones are positive correlations, the blue ones are negative correlations. So this one is negatively correlated, it's somewhere over here, a dark blue. Then we could check these ones on all of these factors and accordingly get these numbers. So we accordingly, you see, these are things which are strongly correlated and positive or negative either way. You can see 0.7, 0.9, all these guys are correlated. These objects you see are not correlated. For example, the distance does not depend upon the mass or the color or the magnitude or the absolute G. These are not related. Hence, you can see these are all, white, close to 0, because these are parameters which are not correlated. If it is these dark blue, dark red, these ones are correlated. And so then these guys are correlated, those ones are not. So heat maps are also very useful to show correlation between factors. Here you can see a regression plot. Supposing I am now, this is a color magnitude diagram actually with a G, BP minus RP. Since this is, simulated data, we are getting data like this. Ideally, we would have not had something like this. But because we have this like this, we can fit it to a straight line and get a regression curve. So these are all straight lines. And generally, this is not how they look. The other factor over here you see is diffractions by groups. So for each of these things, I have a different value for diffraction. Okay, these are the number of objects. So I can actually plot the diffraction for this. And then the important other thing which you did with Sir also was about saving figures. You can save these figures and put it like this. Somebody asked in the morning, and so I would like to also show this thing, is that in principle, right? You may, everyone, all of you all obviously would like to ask the question, what about using AI in plotting, right? So how do you use AI in plotting? So there's absolutely no problem in using an AI in plotting. If you're using Google Colab, the AI thing is there, it's called Gemini, okay? So you can use Gemini. The only important thing is that, for example, you can see in this plot window, I can say generate with AI. So what do I want to generate with AI? I may actually say, what can I help you build? I want to save plot as supposing .png file. Okay, this is what I want it to do. Okay, this is what I'm asking it to do. And therefore what happens, I said save this and I'll say this. So I'm telling that to Gemini. And Gemini, what does it do? It actually gives me the code. How do I plot it? So here it tells me plot figure this thing, scatter plot this thing, this thing, this thing, do this, and it says PLT save fig, and it says this thing and tells me that. Okay, so there's absolutely nothing wrong if you're going to plot it using AI, right? The only difference is that supposing often the plot it may give you is not exactly the one you need, right? Maybe for example, I am not plotting distance versus mass m sun. I want to plot instead distance versus some other factor. Let me look at the other factors. For example, instead of distance, I want to plot it with PM array, okay? Or I want to plot it with BP minus BPRP, right? So I would need to know where in this file do I have to change? What do I change over here so that I can put it like that? Similarly, if I want to change the X label is write ascension dec, but I want to just write RA. So then I will have to change this and I will have to write RA, and I may keep dec because I want to write the units. I may, for example, change my declination to dec, right? So all that you need to do is that even if so I may do that, and now when I run it, I get RA and I get dec. So what happens is, ideally speaking, you can use AI to make your plots, right? But you will notice is that what AI will generate is not exactly the plot you want. You still have to fine tune it a little bit yourself. And therefore, for example, you should be able to understand this code. For example, when I'm saying hue is group, right? I should be able to understand what do I mean by hue by group, because these are the different colors, right? So hence that's put in my different colors. right? But I may accordingly, I may want to make changes. So what you need to do is to be able to read this code and understand what it means, right? For example, this is the legend. This is the legend. This is the position of the legend. Supposing you want to change it, you see this is the legend, which we've said upper left. You have to, if you want to change it, you should know how to change it, right? So that's the deal. There's no harm if you're using AI to do your plotting. The only thing is that you have to know how to read the syntax so that you understand it, so that you can, once you, even if you use the help of AI to plot something, you may see now I've used it, I run this, I plot it, right? This is my plot which has come, but I may then make changes in this according to my liking for whatever I would want to plot. So you should be able to understand what this code means so that you can adjust it to whatever you want. Okay. So there's a short exercise over here. You can try plotting in this exercise. But I want to move to something else, which I'm very keen on that you know, is that it's a very useful thing in Python to use even for Matplotlib and this. There are what I call is a gallery. You have a gallery for Matplotlib, you have a gallery for Seaborn. What is the advantage? You can go into this gallery and you can have a look at plots. Okay. For example, I realize that I do not want vertical bars, but I would like horizontal bars. So you see this one is a horizontal bar chart. I want to know how to draw. You can look at any of these plots, choose a plot you like, and you can do this horizontal one. So I want to know this. You just click on this. It shows you the code. How do I make a horizontal bar chart? Read this over here, and you can see it's written over here. People this performance, and you can see that you see axis is dot bar h. Okay, bar h basically means a horizontal plot. So because I now want my horizontal plot, I have got to write bar h. So the code is given to you here. This is exactly like what we were talking about. If AI gives you the code, so AI or this thing is giving you the code for this plot. Okay. Now what you have to do is adjust these commands which you have over here for your requirement. Supposing you're doing it for different kinds of galaxies of different morphologies. Then over here you have Tom, Dick, Harry, Slim, Jim. Instead of that, you edit it over here and you write elliptical, spirals, lenticulars, whatever the other galaxies you want. You may change it for that, right? So what you basically need to do is to read this and to make changes. You can go back to the gallery and look at any other plot you like. You may like some other plot. For example, you may like this plot, which is, for example, let us look for these plots. You may like, okay. For example, look at this. Contour plotting, the solutions place for optimizations. Okay. So you have, for example, this is a plot, right? And what we basically done, contour plotting, is you take a certain thing and you look for the same value of it, right? And you do this thing and you can actually do it to show the topography of the thing. I'll talk about this a little in another plot. I'll just show one more to you. And you can take it like this. I would like to now instead look at the Seaborn gallery, right? Let's look at the Seaborn gallery. That's a more interesting, fun gallery. So here, for example, this is the Seaborn gallery, right? You may see various plots in this thing and you may find something interesting. Having a look at these plots is very helpful because there could be times where it would actually give you good suggestions as to what are the different values. Like, for example, look at this plot. This is a line plot, okay? Now, in this line plot, what you can see is that you basically have put a line plot for some 3 regions, and you could also put in, for example, the areas. You see this colored part which is put over here. You may plot the response for different events and regions, and you may change the color, right, as per your requirement. You may, for example, want to do box plot, but to doubly do it. So if you want to do it like this, for example, you may have this is like the this is the Python data set, which is called tips. Okay, what is the tips data set? Is on different days you have different people who go to hotels. Okay, so of which, say, the purple ones are smokers, these ones are non-smokers on different days, and you check up what is the total bill on different days. I want to make a comparison about, does the bill have to do with whether people are smokers or not smokers, as well as I want to compare it with the different days of the week. So you can see that the bill is lesser on Thursday and Fridays, smokers, non-smokers. On Thursdays, we notice that the smokers is lesser than non-smokers. On Fridays, we see smoker is about the same, non-smokers slightly eat more. But then you can see a difference on weekends. On weekends, Saturdays and Sundays, you'll see that the smokers have bigger bills than the non-smokers. So these are what we call box plots. If you remember, here's the median. This is Q1, Q3. Here are your whiskers, and here are your outliers. These are your outliers, the zeros. So here you can see this is the code. This is the code to make this plot, right? So what happens with the gallery is that this is the way in which you can become independent, right? In the sense, now you are doing your own work and you want a certain kind of plot. So if you can find that plot or something similar to that plot in the gallery, you can directly see the code. Okay, so instead of AI generating the code for you, this is better, because here you can see the code which is generated for this given plot, and then you can see what changes do you want to make in this code for the plot you want, right? So maybe you are doing it for smoker, non-smoker. You may be doing this even for male, female, for example, or you could vary it for something else. Or the tip, this is the bill, but you may check it for the tip. So you may choose it accordingly, right? Okay, so this is that. Please take use of this thing. One last thing I will show you, and then I will pass it on to Sir, and that is about another very interesting thing which is there, which is called which is called Plotly. Okay, this is yet another one. We've done Matplotlib, we've done Seaborn. Now let's look at Plotly. Plotly is the one which gives you three-dimensional or interactive plots. Okay, so I'm going to use the same data sets we've used. So let us use the first data set where we had our three, you remember our three clusters ABC. Okay, so I will plot that same thing, ABC. Only difference that you'll see in this is that, oopsie, again, the same problem which I had in the morning. Okay, 1 minute, I will just. Yes, morning also had the same problem. So here what it does is, you see, this is interactive. That means now when my cursor moves, I can actually see the values. Okay, I can look at a point and it will tell me the values for that very point based on all the data it has. So that is the interactive part it will do. For example, I can even plot my proper motion diagram. This is proper motion array, proper motion deck, and I've done this. In this plot also, what you can see is that the sizes have been scaled as per the masses of the star. So you can see over here, you can see size, mass, m sun. Okay, so the size is getting scaled as per the mass. So you can see here you have a massive star. This star has a mass of 2.24, while a smaller star, look at this one has a mass only of 0.15, right? So I have this. Diskless disk bearing is differentiated by circle and square, right? So, and the size of the thing is by the mass of the star. A color magnitude diagram also can be plotted, where again you can move this and you can get all the values using this. Histograms also, you see here it's even interesting. I have a histogram here, and I also have a box plot. So look at the box plot. If you remember, this is the median value, this is Q1, this is Q2, these are the whiskers, and here is the outlier, right? So here you can actually see is the distance distribution of all these three clusters, right? There's a violin plot also over here, the violin plot, and I can move this and actually look at the different values at different points, right? So Plotly gives you a chance to interact with your plot. This is a disk fraction plot. Again, you can see the values. But the fun part is here. The fun part is if you have a 3D map, for example, I'm doing a 3D map, I'm converting these stars to X, Y, Zs, then here what you see is I can actually rotate this, okay? I can rotate the Plotly plot and I can look at it from up, down, whichever side I want to see, and I can plot it. For example, here I'm plotting Z versus Y, or I can plot whatever I want, and I can look at it like that. Similarly, here there's a proper motion plot, but a proper motion plot here is only 2D. So if I turn it, there's nothing else, I just get these values. This is not three-dimensional. If it was three-dimensional, I would have got that. And then here there's a nice, another interesting thing which you can do with Plotly is you can actually generate animations. So this is a very simple animation, which is of this movement. So the animation is generated over here. You can see the code. I won't go into the details because we don't have the time, but look at this code over here. Here is the animation thing. So I can run this and you see, basically these stars are just moving up, nothing more. But you can see this is the movement of these individual associations and clusters. So you can move it and you will get it in the form of an animation. So if you look at the code over here, it's generated, this is your stuff, and this is the animation 0.003 into t. This is the value, and that's how you're actually changing this thing, right? But you can generate your own animations within this. Again, a pair plot can be made, and you can export it obviously to HTML or whatever format you want, and you can do it. Please, as homework, you can go through the other data which is there in this. There are exercises over here which will help you to this thing. Okay, I'll hand it over to Sir now because he wants to still do a little bit with you. So I'll stop, and here you can go ahead. Yeah, Najam.
Yeah, so there were a few things which were asked towards the end of the session. Someone had said, in continuous data also, how do we choose the bins, right? So for example, we have this data where we have 1,000 points, and I am plotting with, say, I'll plot it with 3 bins, okay? And when you plot it with 3 bins, you see that this is the kind of thing you are getting. You are not getting a good enough idea, right? Because what is the maximum number from, we are breaking the whole data into 3, and the histogram is not very representative of what we are trying to see. What if I make it, say, 30 bins, right? Sorry, 30 bins. And you see that the dip which we have in the center was not visible in the previous one. You could not see the features here. And see further that if I increase it, say, 200 bins, to 200 bins. And right, you see, so here you can see that there are a lot of gaps and so on. So depending on the data which you have and at what level you want to see the changes of numbers. You have to choose an appropriate one, which will tell you what kind of bins you have to choose. When you use a larger bin, then the largest value which you have for the whole bin will have one single bar on that. Okay. So you have to choose an optimum one, which is very good representative of at a larger level what the data is, right? Second thing I wanted to show was somebody asked, how do we add uh, X and Y uh, labels in these multiplots, right? And what we had to do, I had done it, but for some reason I was getting an error there. So you exactly as you said, title, you have XS and 0, and then you say set underscore X label, and whatever label you want to put, you specify that here, and you get the X label, right? So we have put the X label in the 0th one. Similarly, you can put the Y label here. I repeat the same thing, set Y label and specify what we want to write here. Say sign of X, and you have got X label and Y label, right? Similarly, if we want it for the other one, you will have to do the same thing. Set X label, Y label, and I write it here, and I change this to 1, 1, and I'll change this to say cos, because second one is cos, and you see that you are getting X label, cos, and right. So I did the same thing in the earlier session, but somehow there was an error. So the command is this: which plot you are doing, set X label, set exactly like we had set title, we had done it, right? So this is it.
Can you have them overlap? Yes, you can. Can you have them overlap? You can.
So they have the same.
Can you have them overlap?
Yeah, you can do this. And another thing which I wanted to show is if we have to read data from a file, suppose we have a comma separated variable file, and I have a file here, say, which is of M3. You have arrays, decks, parallax, PMRA, PMDEC, and so on. And I want to read this data. This is comma separated variable, and I want to read this. So I used import pandas as PD. Priya ma'am did pandas earlier. And I use this command df equal to pd dot read underscore comma separated variable, and in inverted commas the name of that file. The name of the file is m3.csv, right? And there is another called creating a profile report. This is a very neat way of doing all basic statistics in one go. So you run this command from y data profiling, import profile report, and I read. See, this is I'm storing it in data file. And if I just run the command profile report of df and I save it into profile, it will create a profile report. And then I'll write that profile to a file, and I'll give the name profile report, say .html. Okay. So once I run it, it takes a while, it's running. And once it is done, so it is done, and you will see that it has created a profile report HTML. And if you look at that report, you will have the whole set of statistics here. There are different tabs here. One is the overview. Number of variables are 6. Number of observations are 36,424. Missing cells, there are certain missing cells. Somebody had asked in astronomy data, can they be missing cells? Yes, look at this. There are so many missing cells here. And the percentage of missing cells are 31%. Whether they are duplicate rows, none. Yeah, so size in memory and so on. Then for each variable, it gives you the uh, statistics for each variable. What is the minimum? What is the maximum? How many zeros are there? How many missing points are there? So in RA, you have 100%. There is nothing missing here, right? And it has plotted the histogram of RA. So here you can, right? In DEC, you have the histogram, right? Then in parallax, it is giving you the histogram. PMRA, PM, so it gives you all the basic ones. Then it gives you interactions. RA against declination. You can see, you know, you can see the whole of statistics. It does correlation, it does heat maps, it gives you a table of missing data. So the whole of statistics is given to you in a report. So just by running a small command, uh, which is profile report on the data frame, you get the whole set of thing. And then profile, this is the name where we have stored. Profile to file, we'll save it into the file. Another thing which I wanted to show to you, which I'll share with you, is is um, yeah. So I'll share this with you, which is a PDF file, which will essentially discuss and show you when do you use a certain file test. For example, yeah. Hmm? So yeah, and I will share with you some other where chi-square tests and Kolmogorov tests are done, and we generate some data uh, and with noise in it, and we do the chi-square test and Kolmogorov's test in this, and also another one, hypothesis testing. How do we do the students' t-test and so on? Um, I think we are running out of time, but this will tell you how to do the t-test and Kolmogorov test and do all the plots, right? So in stats, we have stats.t-test, which will do the comparison between two tests and right. So t-test in induct and it calculates the whole of it. So these are the things we'll share with you. You have a look at it, and we will discuss it in the next class.
You can ask for questions.
If you have any questions, we'll take them. We have last 2 minutes.
Hello.
Yes.
Can I go on with my question?
Yes, yes, please do. Please do.
Yeah. Thank you, Sir Najam, for your wonderful presentation. I want to ask from your slide in when you were trying to explain the hypothesis testing, is it possible to cut a large data into a small group of data and run the hypothesis test, and with the results be sufficient, like will the results be sufficient to justify the large data? That's one question. Um, and again, when you're talking about the Bayesian function, um, can this Bayesian function be applicable, or can we just say is correlated to time series testing? I don't know if you understand my question.
Not exactly.
Yeah,
Can you just repeat it or write it in the text? Yeah.
yeah.
I'm not
I
too sure.
couldn't understand.
My
You can
first
just write
question is,
the.
okay.
Can you write it in the chat?
Just see. No, he's not written. Yeah, Harrison, can you repeat your question? Hello?
Hello.
Yeah, Harrison, can you repeat your question?
So I said in the hypothesis testing
Yeah.
that Sanajam talked about, can a large group of data be split into group of data, and can this small group of data uh, justify, let's say, the whole hypothesis for a large group of
Okay.
data?
Yeah.
Okay.
Yeah.
Yeah. So see, there are different tests which are used to do that. For example, if you have use Kolmogorov-Smirnov test, which is used to compare either two different sets of data and see whether they are significantly similar or different, or you can use the small data set is whether it's a good representative of your population set, right? So depending on whether it's continuous, if it's continuous data, then you use Kolmogorov-Smirnov test, and if it is discrete, then you use the student's t-test to do that, right? Student, if the numbers are less than 30, then it's considered as a small data set, and it is used when we are yeah, so you use the student's t-test to do that. You compare on the basis of your small data set, you say whether it's a good representative of your the population, right? And similarly, there are various tests which do that. One is F test. If the variance is known, then you use the F test. If the variance is unknown, then you use the t test. And similarly, for discrete data, you have uh, the t-test, while if you have continuous data, then you use the Smirnov test. That's what I wanted to show you, but my that file just didn't open here. I will share it with you. In the morning session, we managed to discuss it. This time, where is that file? I'm unable to find the file. I'll share the statistical test. Yeah. Yeah. Okay. So I will share my screen. Yeah. So see, this is the example where if you have category kind of uh, data where the data is discrete, then we use the chi-square test. For example, if you have a galaxy survey which predicts that there are 50% spirals, 30% ellipticals, and 20 regular, but we observe a sample of 20 galaxies where there are 120 spirals, 50 ellipticals, and 30 regulars. That is, rather than 50, there are about 60% spirals, and instead of 50, we have lesser. And then we used the chi-square test to do that. The Kolmogorov-Smirnov test, KS test, is used when you are comparing these continuous distributions. And for example, we have astronomers measure brightness values of 500 stars in a cluster. And the theory, right? So all these tests are parametric ones where you have an underlying theory and you are testing that from the sample which you have. For small samples, we use different tests, and for large samples, we use different tests, right? And discrete data, we use different, and for continuous data, we use different. So in this document which I have here, I will show you, I have discussed when each test is used, and I will share it with you in the chat right now. And yeah, on the basis of your small sample, uh, you can predict, you can say, talk about the whole population, but you cannot in 100% say that this is what it is. Statistics tell you at what level of significance a certain assertion you are making is right or wrong. So you calculate the p-values and you compare what you have calculated, check with the table values, and on the basis of that, you conclude that your sample is a good representative or not, right? And at what level of significance, right? So yeah, it can be done, and it is done in statistics because there's not a we are using statistics because we can't uh, get each and every object in the whole universe of that type to study it. We are just seeing a small sample, and on the basis of sample, you try to predict and you try to assert certain things, right? So yeah, it can be done.
Okay, thank you. Hello?
Yes.
Yeah, thank you for your answer. If I get you clearly, you said it can be done, but we have to justify using the statistical method for justification.
Exactly. Yeah. So it can be done. And you
All right, sir.
use statistical justification to assert what you are saying and on what basis are you specifying it is done. And it is become very essential now to use these statistical tests, which are very robust, to actually uh, give out your results, right? And you specify also the level of significance, at what level of confidence are you stating what you are stating. Yeah. Okay, so if there are specific questions, you can write to us and we will answer them in our next sessions, specific ones. And if there are no more questions for now, we'll stop now because we have gone beyond the time.
Yes, thank you very much, Najem. Yes, I think I've gone beyond time. So I think I would suggest that participants should go through their materials for week 3. If you have any questions, you can ask in the communication channel. Remember, the most important thing is for you to focus on the learning materials. Run the example notebooks and try and do your exercises. That's the only way you will learn. Thank you very much. Do
Lebo,
enjoy
you
the
can close it. I think we are overshot. We've overshot time.
Yes.
Thank you.
Yeah. So we'll
Thank you.
see you
Bye-bye.
again next week. Bye, everyone.